Welcome friends to my YouTube channel. Now in previous lecture I shall discuss about low temperature physics, and there I told about Joule-Thomson porous plug experiment, and also I have find out the value of Joule-Thomson coefficient, that is increase in temperature per unit pressure keeping enthalpy constant. Now in today's lecture I shall going to discuss the various cases. Okay, that is we take the example of ideal and real gas. Okay, so first of all today I shall take the example of ideal gas at first, and let's see what happens for ideal gas. Now we know that the expression of Joule-Thomson coefficient can be written in this form: 1 by Cp T into del V del T pressure constant minus V. Okay, so JT coefficient can be written in this form. Okay, now for perfect gas what happens? 1 mole perfect gas we always write. Now what happens if we differentiate this expression with respect to T keeping volume constant? This is simply this. Now what will be the value of del V del T pressure constant? My del V del T pressure constant is R by P. Okay, del V del T pressure constant, this is equals to R by P. So this is simply 1 by Cp. You put this value, that is RT upon P minus V. Okay, now this is simply 1 upon Cp. What is RT by P? That is V. V minus V, that is 0. So we see that for a perfect gas there is neither heating nor cooling, that is Joule-Thomson coefficient vanishes. Okay, so for perfect gas, there is neither heating nor cooling. Okay, so we see that for a perfect gas there is neither heating nor cooling because the value of mu comes out 0. Okay, so this is the value of mu for perfect gas. Okay, now let us take the example of 1 mole real gas and let's check what will be the value of mu for real gases. Okay, now we all know that for 1 mole real gas van der Waal equation is this. This is simply RT. Okay, now multiply it, PV minus PB plus A by V minus AB by V square. This is simply RT. Okay, PV minus PB plus A by V minus AB by V square. This is equals to RT. So differentiate this expression with respect to T keeping P constant. So what happens? P into del V del T pressure constant, P constant and B constant, so this term 0 minus A upon V square, and since we are doing with respect to T, this term 1 by V square minus 2 by V cube, so my plus 2AB by V cube. This is simply del V del T pressure constant. This is equals to R. Okay, so what will be my del V del T pressure constant? My del V del T pressure constant will be simply R by P minus A by V square plus 2AB by V cube. Okay, P minus A by V square plus 2AB by V cube. Okay, kindly ignore the new noise which is coming from outside. So you can write this term as P plus A by V square minus 2A by V cube into V minus V. Okay, P plus A by V square minus 2A by V cube into V minus B. Okay. Now you substitute P plus A by V square, you put RT upon V minus B minus 2A by V cube into V minus B. Okay. So you can write here up to this. Okay. Now if we simplify it more, then we get what? Del V del T pressure constant. This we get R upon, if we take RT upon V minus B common, okay, then we get 1 minus, this term will become 2A by RT V cube V minus B whole square. Okay. Now R cancels, so this term becomes V minus B by T. Okay. And this becomes 1 minus 2A by RT V cube into V minus B whole square to the power minus 1. Okay. Now so if we expand this, then this become V minus B by T. This becomes 1 plus 2A by RT V cube into V minus B whole square. Okay. This becomes this. Okay. Now we can neglect this B square term with respect to V. So what we get? We get V minus B by T. This is simply 1 plus 2A by RT V. Okay. Because here we use this approximation, V is very much greater than B. Okay. This approximation is used by me. So this is the value of del V del T pressure constant for 1 mole real gas. Now if we substitute this value in the expression of mu, then what the value of mu comes out? The value of mu comes out 1 by Cp T into del V del T pressure constant. That means V minus B multiplied this, V minus B into 1 plus 2A by RTV minus V. Okay. So what this becomes? 1 by Cp. This is V and this is 2A by RTV. That means 2A by RT minus B. Okay. Neglecting the product term, that is 2AB by RTV, this term is neglected, so the value of mu becomes 1 by Cp 2A by RT minus B. So this is the value of mu in case of a real gas, and moreover this relation is used to find out the value of inversion temperature of a gas, and we will discuss it later. Okay. Now you know that this relation is used to calculate the value of Ti, that is inversion temperature for different gases. Okay. Okay. So this is the value of Joule-Thomson coefficient for a van der Waals gas. Okay. Now one thing you remember, that mu, we find mu as 1 by Cp into 2A by RT minus B. Now a close look to this equation shows that both van der Waals constants are involved here. Okay, both A and B is involved here. Now there arises three cases. Okay, what are they? First of all, if you assume that intermolecular force of attraction is very strong, that is A very much greater than B, then what happens? Mu is positive, mu is greater than 0, and mu means what? dT dP. Okay, dT dP greater than 0. Now in JT coefficient, I previously told that the gas flows from a region of high pressure to a region of low pressure. That means final pressure is less than the initial pressure and the change in pressure is negative. So dP is negative. So in order to become dT positive, dt must also be negative. Okay, so when mu greater than 0, dt is negative. That means cooling occurs. Okay, so cooling occurs. Okay, because in JT coefficient, JT porous plug experiment, dt is always negative. In order to become mu positive, dt must be negative, so cooling occurs. Second case, now if the intermolecular force of attraction is small and volume correction term dominates, that is B very much greater than A. So if volume correction term dominates, then this term is greater, so that mu will be negative. Okay, so my dt dp will be negative, dp is always negative, so dt will be in this case positive. So the gas warms up. Okay, gas warms up. Okay, so the gas becomes warm. Now another case, if mu is greater than 0, then what happens? For mu is equal to 0, what happens? 2a by rt, this equals to b. 2a by rt, this equals to b. Okay, so from which we can easily find T, this is equals to 2a by br. Now this is called the inversion temperature. This is the expression of inversion temperature. For mu equals to 0, this term becomes 0, so T will be 2a by br, and this is called what? This is called inversion temperature Ti. Okay, this is called inversion temperature. Okay, so this is the expression of inversion temperature. Okay, so the temperature at which the gas neither shows heating or cooling. The temperature at which the gas neither shows heating nor cooling is called, okay, the temperature at which the gas neither shows heating nor cooling is called inversion temperature, and it is denoted by Ti. Okay, the temperature at which the gas neither shows heating nor cooling is called inversion temperature, and its value is what? Ti, this will be 2a by br. Okay, now we can easily find out a relation between inversion temperature and critical temperature. We know what is critical temperature. It is the temperature above which a gas cannot be liquefied by mere application of pressure. Okay, so critical temperature is that temperature above which a gas cannot be liquefied by mere application of pressure. That means up to T equal to Tc, the gas can be converted into liquid. Beyond this, conversion is not possible. Okay, so the value of critical temperature we all know, that is 8a by 27 br. We will do it in real when I will teach heat van der Waals chapter. We will do it. Okay, so Tc will be 8a by 27 br. So divide this. So what we get if we do Ti by Tc, then what happens? This is simply 2a by br. this goes 27 br and this is 8a. Okay, this is 8a, so br cancels, a cancels, and this goes 4. So that means 27 by 4, that means 6.75. 6.75. Okay, or you can say 27 by 4, no problem. So this is the relation, that is inversion temperature. This is 27 by 4 into critical temperature. Okay, so this is the relation. So the marker is almost finished. So with this I finished today's lecture. So today we will see the value of JT coefficient for different gases, and we shall find the value of inversion temperature, and we also establish the relation between inversion temperature and critical temperature. Okay. Now in our next class we shall do few other issues related to Joule-Thomson porous plug experiment. Okay, so dear guys, kindly subscribe my channel to get latest videos, and if you have any queries then just write it in comment section, and the video link will be given in the description box. Okay, so thank you.